Hello everyone, I am Aritra from ETH Zurich and today I am going to present our paper ProximiTEE Hardened SGX Attestation using auxiliary device and ProximiTEE verification. The main motivation of our paper is trusted execution environment such as Intel SGX that bring additional security guarantee to traditional platforms. If we look at the traditional platforms, it consists of hardware, for example your CPU, DRAM, other peripherals. On top of the hardware, operating systems are there that manages memory, that has device driver that manages other peripherals, and on top of the operating system you have your apps. Now in order to make sure that your apps are running properly, you also have to trust the operating system on hardware. So potentially your TCB has app operating system on hardware, which is potentially millions of lines of code and huge attack surface. Compared to traditional platform, Intel SGX changes the trust model differently. It enables enclaves or specific apps that are managed by the Intel SGX processor through certain instructions that enables this enclave to be completely isolated from the app and the operating system, so they cannot interfere with the memory space. We assume that the operating system and the other apps could be completely attacker controlled, and we only have to trust the enclave and the hardware. So compared to the traditional platform, our TCB is only the enclave and the hardware. Another important feature of Intel SGX is the remote attestation that ensure that user can verify the enclaves they are running on the platform. For example, you have your Intel CPU that comes with a key that is burned into the fuse during the manufacturing process that proves that you are actually in possession of a legitimate Intel processor. You have your enclave. Now as a verifier, she wants to know that whether this enclave running on the processor is legitimate or not. So the verifier issues a challenge. The Intel SGX CPU produces an attestation report that contains the code, stack, heap and the microcode version number. After that, the CPU signs the attestation report with its key and send it back to the verifier. After the remote attestation process, the verifier learns the following. 1. She is interacting with a legitimate Intel SGX processor. She is also interacting with a legitimate enclave that is running on that processor. And third, the platform public key, so that she could now build a secure channel with the enclave. And after that, she assigns her sensitive data to the enclave. But now as you see that the verifier only learns that she is talking with a legitimate platform, and this is a feature of the EPID or enhanced privacy identifier that hides the CPUs from the user. So user really don't know which specific processor they are talking with, and this can be exploited, and this is commonly known issues. And the specific attack we are talking about here is the relay attack. So let's look at the relay attack a little bit more in detail. So you have your platform that is where the operating system could be temporarily exploited by the attacker. You have the other apps which could be also attacker controlled, and other side of the planet the attacker is in possession of his own platform that is permanently attacker controlled. Now as a verifier, you want to know that whether the enclave you are interacting with is a legitimate platform, legitimate enclave or not. So you issue a challenge, but rather than computing the attestation report in the target platform, the target platform relays the challenge to the attacker's platform. Now the attacker platform computes the attestation report there and send back the signed attestation report back to the target platform, and the target platform hands over the signed report to the verifier. Now verifier thinks that she is actually attesting this platform, right, the target platform, and getting the public key of the target platform, but in turn she is actually attesting the attacker's platform and getting the public key from the attacker's platform. So at the end, when she assigns the secret, it get assigned into the target platform, not to the to the attacker platform, not to the target platform. So one may think that what are the implications of a relay attack, or whether this is really dangerous or not. Apparently this is also our first contribution of the paper to understand what kind of implications relay attack have. So first problem is that the attacker fully owns his platform, so he has unlimited time to do physical side channel attack on this platform. that could extract secret from the enclave. On top of that, as the operating system is fully attacker control, so he could do the privilege escalation attack on his own platform, which may not be possible on the target platform, because target platform could be maintained properly, where the user may install proper security patch all the time. So privilege escalation attack is one of a problem which is exposed through relay attacker. And of course, due to this, the attacker could undermine all the platform maintenance done by the platform providers. For example, a data center, they install security patches and fixes all the time, but doing relay attack, attacker could simply defer all the patches on his own platform. And we little bit talk more in details in the paper, so please refer to it to know more about this subtle cases. Now what we are looking at the relay attack is as the following. So there are a bunch of communication happening between the verifier, target platform and the attacker platform, and these red arrows are extra on top of this black communication, which only should be happening in a benign case, right? But the problem is that all these communications are happening on top of a multi-hop network. So for a verifier, it's impossible to know whether there is some extra communications or not, due to some deviations happening in the network. So to solve that, our next contribution of the paper is to introducing an auxiliary device that is located with the target platform and connected physically, for example with a USB or a Thunderbolt interface. That also comes with a key to know that you are talking with a proper device, and we call this small device as ProximiTEE, that has a very small TCB. Due to this key, the verifier and the ProximiTEE can establish a secure channel. Now if you look little bit closely, we can see the communication between the ProximiTEE and the target platform. On behalf of the user, the ProximiTEE issues the remote attestation challenge, and it gets back the attestation report and the public key of the platform. And using the public key of the platform, it creates the secure channel, and over the secure channel it issues a challenge. The target platform have to compute in order to get the response of the challenge and sends the response back to the ProximiTEE. Now what ProximiTEE does is to calculate the latency between issuing the challenge and getting the response, and it sees based on the latency whether it's physically connected to the to this platform or not, and based on that it determines that whether there has been a relay attack or not. Now if we look at the big picture, if there would have been a relay attack, so ProximiTEE sends the challenge to the target platform, which relays to the attacker platform. Attacker platform computes the signed attestation report, send it back to the target platform and back to the ProximiTEE. Now it calculates the response and sees that the latency is more than the threshold, because it not only includes local interface communication but also the network communication, which is much slower compared to this interface, and based on that it determines that there may be a possible relay attack. Now irrespective of whether there is a relay attack or not, the key always sends the signed ProximiTEE result back to the verifier, saying that whether it thinks if it connected physically to the platform or there has been a relay attack, along with the signed report. So using this, the verifier learns the following on top of the traditional remote attestation is: 1, she is talking with a specific legitimate platform, so whether this platform or this platform based on the ProximiTEE result. And second is that the verifier is talking with a legitimate enclave running on a specific platform. So she also knows that the whether enclave is running here or here. So there is now identity assignment. Now we are simulating a powerful attacker to know how the ProximiTEE verification works in the real life. So in a real world attacker scenario, the attacker would be geographically separated from the target platform, so there would be a multi-hop network that introduces a lot of delays. But we are simulating a powerful attacker to know that what could be the upper bound. So we are connecting our attacker to the legitimate platform with a 1 meter long Ethernet cable, and we are assuming that the powerful attacker could do instant computation, and he also has a network card that virtually has zero latency. And we are also running the network in a ping flood mode that reduces the round trip time significantly to 158 microsecond. So all of these we are doing to make sure that even with such powerful attacker we can distinguish a relay attack and a legitimate connection. So when you put our system to the real world, it will even perform better, because in the real world the attacker has much lesser power compared to our simulated powerful attacker. Now just look at the setup as just I described. So we have the attacker platform, target platform, they are implemented on Intel NUC, connected over a 1 meter long Ethernet cable. ProximiTEE is connected to the target platform over USB 3.0 interface. ProximiTEE is fully implemented based on a Cypress Easy USB 3.0 development board, and we also have a ProximiTEE API that enables the enclaves to communicate with this key, and this API has very few lines of code, so this just facilitates the communication channel. Now if we look at the experimental result, we see two latency histograms. So the yellow one is the local USB interface, and the black one is rerouting over Ethernet, and we can see there is some separation between them, but there is also some overlap because this attacker is actually very fast. As you see, the latency only about few hundred microseconds. So the local USB connection averages around 185 microsecond, while the Ethernet connection, so this 1 meter long Ethernet over ping flood mode, have around 264 microseconds. So there is some difference, but there is also some overlap. And if you see, we say there is some threshold values, and ProximiTEE uses this threshold value to assign certain confidence factor to distinguish between a legitimate local USB connection versus a relay attack. So we have few million samples to make sure that our result is actually robust and is consistent. On top of that, the ProximiTEE and the target platform, they execute several rounds of a challenge response protocol, because one single round of challenge response may have some variation due to this is a local USB connection. So if you have multiple rounds, you can assign more certainty that whether you are talking with a connected platform or not. Now we see this increasing number of rounds effect on the result. So the blue line is the success probability for a platform in ProximiTEE connected over USB, and the red one is the attacker success probability that is over the 1 meter long Ethernet cable. And if we see with the increasing amount of rounds, the confidence in platform in ProximiTEE increases significantly compared to the attacker's one. So if we see the blue one, it's very high number, right, close to 1, while platform that is connected, the attacker platform that is connected over the Ethernet cable is only 10 to the minus 34 over 50 rounds. So attacker has really low chance of convincing you that there is no relay attack. So in real world, ProximiTEE is actually robust and secure. So we thought of several potential use cases where ProximiTEE could be used in real world. For example, trusted IO with the enclaves in a data center is an important feature. So data center, there are several SGX platform, and you want to know that you are talking with a certain SGX platform because maybe you are in Europe, you want to abide by the GDPR. So so you want to connect with this specific data center that is located inside Europe, not outside the continent. So for example, user can communicate with this specific data center SGX enclave and check that whether the ProximiTEE is actually connected to this platform or not, to distinguish that whether he is actually talking with this enclave. And then afterwards the remote attestation, the user can do her trusted IO communication with this specific enclave. Same thing also goes for the permission blockchain. So the consensus node can connect with a ProximiTEE, and the authority could verify that whether they actually have this ProximiTEE or not, to make sure that certain platforms can able to do this permission blockchain consensus process, and afterward they go in the consensus round. So this is one way to make sure that participation is closed. So in conclusion, we look at the Intel SGX remote attestation, that is an important feature of the trusted execution environment. And based on that, we saw how the relay attack is possible, what are the implications of the relay attack and the analysis of it. And we have a ProximiTEE that leverages distance bounding and trusted embedded device to certain the closeness to a specific platform. We also implemented it and we saw this is robust against the relay attacker and is very practical. Thank you very much for your attention, and I am up for questions.